In the vast expanse of the cosmos, where do we begin? That's a question that has baffled humans for centuries, sparking curiosity and leading to the exploration of the universe. Welcome, dear seekers of knowledge, to this enlightening journey where we delve deep into the mysteries of the cosmos, beginning with the very birth of our universe. We're introducing a series that embarks on an exploration of the universe's inception, its evolution, and the principles behind its existence. To kickstart this adventure, we turn our gaze to the Big Bang, the leading scientific explanation for the creation of the universe. This theory suggests that our universe originated from a singularity, a point of infinite density and gravity, around 13.8 billion years ago. This event set the stage for the formation of galaxies, stars, planets, and everything we see around us today. So, buckle up as we journey back to the very beginning of everything. The universe didn't always exist as we know it now. It had a beginning, a starting point. Believe it or not, everything we see around us, the stars, galaxies, planets, and even the vast emptiness of space began from a single point. This is the core idea behind the Big Bang theory. Imagine a dot. Now this is not your average dot. It's smaller than the point of a pin, yet contains all the energy, matter, space, and even time. This is what we call a singularity, a point of infinite density and heat. Unfathomable, isn't it? Yet, this was the state of our universe around 14 billion years ago. The Big Bang theory proposes that this singularity, under immense pressure and heat, started to expand. And when I say expand, it wasn't a regular expansion. It was an event where the very fabric of space and time began to stretch, carrying energy and matter along with it. Now you might be wondering, where did the singularity come from? Well, that's a question that even the brightest minds are still grappling with. Some theories suggest it might be a result of quantum fluctuations, while others propose a cyclic model of the universe. But the exact origins remain a mystery, a question mark at the very start of our cosmic story. As the universe expanded, it cooled down. From this cooling, energy started to convert into particles of matter and antimatter. These particles and antiparticles in their frenzied existence kept annihilating each other, releasing pure energy. But for reasons we still don't quite understand, there was a slight excess of matter over antimatter. And this excess matter, well, it went on to form everything we see in the universe today. But the Big Bang wasn't a chaotic, disorderly event. It followed the laws of physics, even if those laws were a bit different in the extreme conditions of the early universe. For instance, the universe didn't expand at a constant rate. It went through periods of slower and faster expansion, a concept we'll delve into when we discuss cosmic inflation in the next scene. Before we wrap up, it's important to clarify a common misconception. The Big Bang was not an explosion in space, but rather an expansion of space itself. It wasn't an event that happened at a particular spot in the universe. Instead, it was an event that happened everywhere at once, because at that time, everywhere was the same place, the singularity. So, in a way, we're all children of the Big Bang, made from the remnants of that primordial singularity. The Big Bang was not an explosion in space, but rather an expansion of space itself. From the fiery chaos of the Big Bang, the universe as we know it began to take shape. Picture this, an infant universe, a sea of hot, dense particles and energy, expanding rapidly. As the universe cooled down, these particles started to clump together, setting the stage for the formation of the cosmic structures we see today. Gravity, the great sculptor of the cosmos, began to pull these particles together. The areas with a slightly higher concentration of particles attracted even more particles, thanks to gravity's pull. These clumps of matter eventually grew dense and hot enough to ignite the nuclear fusion reactions that power stars. And so, the first stars in the universe were born, lighting up the cosmic dark ages with their fiery brilliance. Around these stars, disks of gas and dust began to form. Over time, these disks coalesced into planets, moons, asteroids, and comets, creating the diverse array of planetary systems we observe in our galaxy and beyond. Meanwhile, on a larger scale, gravity was also shaping the grand architecture of the universe. It pulled together vast amounts of matter to form galaxies, colossal structures made up of billions of stars bound together by gravity. Some of these galaxies group together to form clusters, and clusters connected with each other through filaments of galaxies, creating a vast cosmic web. This cosmic web is the large-scale structure of the universe, a testament to the intricate interplay of matter, energy, and gravity. It's a complex network of galaxies and dark matter, stretching across billions of light years with vast voids in between. Each point of light in this web represents a galaxy, each galaxy a collection of billions of stars, and around many of those stars there might be planets, some of which could potentially harbor life. Our own Milky Way galaxy, our solar system, and our home planet Earth are all part of this cosmic web. We are the products of cosmic evolution, of countless eons of gravitational choreography and nuclear fusion, of particles and forces set in motion by the Big Bang. To understand the formation of the universe is to unravel the story of our own origins. It is to comprehend how we came to be, how from a hot, dense point of singularity, the universe expanded and cooled. Matter clumped together under gravity's pull, stars ignited, planets formed, and galaxies spun into existence. Over billions of years, the universe has evolved into the complex web of galaxies, stars, and planets we see today. The cosmos continues to expand, to change, and to create new stars and planets. As we look up at the night sky, we are not just stargazing, we are looking back in time, witnessing the ongoing story of the universe, the grand cosmic drama in which we are all participants. In the first moments after the Big Bang, the universe underwent a rapid expansion known as inflation. Imagine a balloon expanding at an unimaginable speed, but instead of air filling it up, it's the fabric of the universe itself stretching and growing. This period of inflation happened in less than the blink of an eye, but it set the stage for everything that would follow. Cosmic inflation is a cornerstone of our understanding of the early universe. It's the process that smoothed out the wrinkles and bumps in the fabric of space-time, setting the stage for a universe that looks roughly the same in all directions. But what caused this incredibly rapid expansion? That's still a matter of ongoing research. Some theories suggest it was a kind of energy field, while others propose it was a quantum fluctuation on a grand scale. The details are still being worked out, but the evidence for inflation is strong. And what is this evidence? Well, it comes from something known as the cosmic microwave background, or CMB for short. The CMB is the afterglow of the Big Bang, the oldest light we can see in the universe. It's a snapshot of the universe when it was just a few 100,000 years old, long before stars and galaxies began to form. This light has been traveling through space for nearly 14 billion years, and it carries with it a wealth of information about the early universe. When we look at the CMB, we're looking at a kind of cosmic baby picture. It's a testament to the power of science that we can gaze back through time and space to see the universe in its infancy. When the universe was still young, it was a hot, dense soup of particles. As it expanded and cooled, these particles began to combine to form atoms, and the light that had been bouncing around was finally free to travel across the universe. That light is the CMB, and it provides a kind of cosmic background noise that pervades all of space. The CMB isn't just a relic of the past, though. It's also a tool for understanding the universe's future. By studying the tiny fluctuations in the CMB, scientists can learn about the distribution of matter in the early universe, which in turn helps us understand the structure of the universe today and predict how it might evolve in the future. The cosmic microwave background is our window into the universe's earliest moments, a snapshot of the Big Bang itself. It's a testament to our curiosity and ingenuity that we can reach back across billions of years and catch a glimpse of our universe's fiery birth. In the grand cosmic story, the CMB is a crucial chapter, one that continues to inform and inspire our quest to understand the cosmos.
Imagine a vast cosmic dance choreographed by gravity and inertia. This is our solar system, a fantastical spectacle that unfolds over a stage so grand it's difficult to fully comprehend. Our solar system, a divine masterpiece of cosmic proportions, is a complex mosaic of celestial bodies, all playing their part in this grand ballet of the cosmos. Our solar system is but a tiny corner of the Milky Way galaxy, nestled in one of its spiraling arms. It's an awe-inspiring neighborhood, teeming with an array of celestial objects. At its heart, a star, our sun, holds everything together, its gravitational pull keeping all its celestial companions in check. Dancing around it are 8 planets, each with its own unique story to tell. From the searingly hot rocky worlds of Mercury, Venus, Earth, and Mars, to the gas giants of Jupiter, Saturn, Uranus, and Neptune, each planet is a world unto itself, with its own unique set of characteristics and mysteries waiting to be unraveled. But the solar system isn't just about the sun and its planets. It's a cosmic jigsaw puzzle that also includes moons, asteroids, comets, and dwarf planets. Some of these moons are worlds in their own right, with fascinating geological features and even the potential for life. Asteroids and comets, remnants from the formation of the solar system, are like cosmic time capsules offering clues about our cosmic past. And then there are the dwarf planets, these fascinating worlds that defy conventional categorization. Each component of our solar system, from the smallest asteroid to the largest gas giant, orbits the sun in a delicate balance of gravity and inertia. It's this intricate dance, this cosmic ballet that has been ongoing for over 4.5 billion years. And it's this grand spectacle that we're a part of, as we hurtle through space on our pale blue dot, Earth. So, as we embark on this journey of discovery, let's remember to appreciate the scale, the complexity, and the sheer beauty of our solar system. And at the heart of this cosmic ballet lies our star, the Sun. Our journey begins with the Sun, a fiery cauldron of nuclear fusion and the inner rocky planets. The Sun, the heart of our solar system, is a hot ball of glowing gases. It's not just any star, but a perfect sphere of hot plasma, intertwined with magnetic fields. It's the Sun's gravity that keeps everything in its place, from the smallest specks of dust to the largest planets. The Sun isn't just a static ball of fire. It's a dynamic, active star with a life of its own. It has solar flares, eruptions of energy that can be seen from Earth, and sunspots, dark patches that are cooler than the surrounding areas. These phenomena are not just beautiful to observe, but also play a crucial role in shaping the space weather that affects our planet. Now, let's shift our focus to the inner planets, starting with Mercury, the closest planet to the Sun. Mercury, a small cratered world, is a place of extremes. It swings from blistering daytime temperatures to frigid nighttime cold. Next up is Venus, often called Earth's evil twin. With a super dense atmosphere and surface temperatures hot enough to melt lead, Venus is anything but hospitable. Then we have our home, Earth, the blue marble. It's the only planet we know of that harbors life, a testament to its perfect conditions. Last but not least, we have Mars, the red planet. Known for its iron-rich dust that gives it a reddish appearance, Mars is a world of vast deserts, towering volcanoes, and deep canyons. Its potential for past or present life has always intrigued scientists. From fiery Mercury to the red plains of Mars, these inner planets each tell a unique story. They're a testament to the diversity that exists within our solar system, a constant reminder of the vastness of the universe that lies beyond our blue home. Beyond the asteroid belt, we find the gas giants, the behemoths of our solar system. These are the outer planets, Jupiter, Saturn, Uranus, and Neptune. Each one is a world unto itself, with unique characteristics that continue to captivate our curiosity. Jupiter, the largest of them all, is more than 11 times the diameter of Earth, boasting a strong magnetic field and dozens of moons. Its most recognizable feature is the Great Red Spot, a storm that's been raging for at least 300 years. Next in line is Saturn, the jewel of our solar system. Its breathtaking rings are made from countless particles of ice and rock, some as small as grains of sand and others as large as mountains. Saturn's largest moon, Titan, is even bigger than the planet Mercury. Uranus, often referred to as the sideways planet, is unique for its tilted axis, causing it to spin on its side. It's a pale blue world due to the presence of methane in its atmosphere, which absorbs red light and reflects the blue. Neptune, the furthest planet from the Sun, is a deep blue world known for its strong winds. Some of the fastest winds in the solar system have been observed on this planet, reaching speeds of up to 2,000 kilometers per hour. But the outer reaches of our solar system don't end with these gas giants. Beyond Neptune, we find a region known as the Kuiper Belt, home to icy bodies and dwarf planets like Pluto. Once classified as the 9th planet, Pluto was redefined as a dwarf planet in 2006. Despite its small size, Pluto has 5 known moons and an atmosphere that expands when it comes closer to the Sun. And let's not forget the countless asteroids and comets that whiz around our solar system. These celestial nomads carry within them the ancient history of our solar system, waiting to be discovered. From swirling gas giants to icy dwarf planets, the outer reaches of our solar system are a testament to the diversity of celestial bodies. But planets do not dance alone. They are accompanied by their moons, each with their own unique rhythm. As we journey further into our solar system, we encounter not just planets, but an array of moons, each as varied and fascinating as the planets they orbit. The first moon that comes to mind for most of us is our very own moon, the only celestial body beyond Earth that humans have set foot on. It's our constant companion, lighting up our night skies, controlling our tides, and even stabilizing our planet's wobble. But our moon is just one among many. Venture out to the gas giant Jupiter, and you'll find a family of 67 known moons. One of these, Europa, is particularly intriguing. It's an icy world that may harbor a subsurface ocean twice the volume of all of Earth's oceans combined. This tantalizing possibility makes Europa a prime target in the search for extraterrestrial life. Then there's Titan, the largest moon of Saturn and the only moon in our solar system with a substantial atmosphere. Its dense, nitrogen-rich atmosphere and the presence of surface lakes and rivers of liquid methane and ethane make Titan a world that both resembles and starkly contrasts with our own. Yet, it's not just natural moons that catch our interest. Human-made satellites also play a pivotal role in our exploration of the cosmos. These spacecraft, from the iconic Hubble Space Telescope to the Mars rovers, have expanded our understanding of the universe far beyond what we could achieve from Earth alone. The audacious voyages of these spacecraft, venturing out to distant moons and planets, embody our collective curiosity and our relentless quest for knowledge. They've beamed back stunning images and invaluable data, revealing the beauty and complexity of our solar system. From the familiar face of our moon to the mysterious oceans of Europa, moons offer us a glimpse into the extraordinary variety of worlds in our solar system. So let's keep exploring, keep questioning, and keep reaching for the stars. For every answer we find, a new question awaits, reminding us that our journey through the cosmos is far from over. Our solar system is a cosmic wonder, a testament to the grandeur and diversity of the universe. As we've journeyed through this celestial neighborhood, we've encountered the fiery majesty of the Sun, the nucleus of our solar system. Its phenomenal solar flares and constant nuclear reactions fuel life as we know it on our own planet, Earth. Speaking of which, Earth, our blue marble, is just one of the inner planets. Mercury, the smallest and closest to the Sun, and Venus, our scorching and volcanic next-door neighbor, remind us of the variety that exists even within our immediate vicinity. Then, there's Mars, the red planet, a testament to the universe's ability to surprise and intrigue us with its potential for past and future life. Venturing further afield, we've met the gas giants, Jupiter and Saturn, a pair of behemoths with their own miniature systems of moons and rings. Beyond them, Uranus and Neptune, the ice giants, display the extreme conditions that exist at the edges of our system. Let's not forget the dwarf planets, asteroids, and comets, the small but significant players that add depth and complexity to our solar system. From Pluto, the most famous dwarf planet, to the myriad of asteroids in the belt between Mars and Jupiter, they all have stories to tell. We've also explored the moons of our solar system, from our own familiar moon to the exotic satellites of other planets. These moons, like Jupiter's volcanic Io and Saturn's icy Enceladus, continue to challenge our understanding of what it means to be a world. As we journey through this grand tour, let's remember the scale of our solar system. It's vast, diverse, and full of wonders waiting to be discovered. Yet, it's just a tiny part of the universe, a single system in a galaxy of billions. As we explore these celestial bodies, we not only uncover the secrets of our universe, but also of our place within it. This is our cosmic neighborhood, our solar system.
Imagine floating in the vast expanse of space, gazing upon an ethereal spiral of stars, gas, and dust. This is our home, the Milky Way galaxy, a cosmic city teeming with about 400 billion stars, Our galaxy is a swirling spiral of light and darkness sprawled across a breathtaking 100,000 light-years. This celestial cityscape is divided into three main parts: a bulging center, a flat disk with spiral arms, and a surrounding halo. And nestled within one of these spiral arms, at a comfortable distance from the bustling galactic center, lies our solar system, a tiny speck in the grand scheme of things. But even as a speck, we've managed to unravel some of the secrets of this cosmic metropolis. As we delve deeper, prepare to embark on a journey through the cosmic labyrinth of the Milky Way. The Milky Way, a barred spiral galaxy, flaunts a structure as complex as it is beautiful. At the heart of this complexity lies the galactic center, a bustling hub of celestial activity. Hidden beneath the cosmic dust and gas, a supermassive black hole known as Sagittarius A** resides. It's a region of intense gravitational pull, where stars whiz around at astonishing speeds, their paths traced out by the irresistible pull of the black hole. Straddling this galactic center is the bulge, a tightly packed spheroidal region filled with stars, both young and old. The bulge is like the downtown of our galaxy, where stars live in close quarters, constantly interacting and influencing each other. Stretching out from the bulge are the galaxy's spiral arms, grand structures that give our galaxy its distinctive shape. These arms, named for the constellations they point towards, such as Perseus and Sagittarius, are sites of active star formation. They're like celestial nurseries where clouds of gas and dust collapse under their own gravity to birth new stars. But the spiral arms and the bulge aren't the only components of the Milky Way. Extending beyond the well-lit world of the spiral arms is the galactic disk. This relatively thin, flat region is home to the majority of the galaxy's stars, gas, and dust. The disk is like the suburbs of our galaxy, where life is less crowded and stars have room to breathe. Yet even beyond the disk, the galaxy doesn't end. Surrounding the entire galaxy is an invisible component called the halo. This vast spherical region extends tens of thousands of light-years beyond the visible galaxy. The halo, largely made up of dark matter, is a bit like the countryside surrounding a city. It's sparsely populated, hosting only the oldest of stars and globular clusters, spherical collections of stars that orbit the galaxy's center. Each component of the Milky Way, from its bustling center to its serene halo, plays a critical role in the galaxy's structure and evolution. The galactic center, with its supermassive black hole, dictates the orbits of stars and gas in the inner galaxy. The spiral arms, with their ongoing star formation, contribute to the galaxy's growth. The disk, with its vast star population, gives the galaxy its flattened shape. And the halo, with its dark matter, provides the gravitational glue that holds the galaxy together. All these elements, interacting and influencing each other, create a dynamic, ever-evolving system. A system that is not only home to our solar system, but also to hundreds of billions of other stars, each with their own planets and moons. This intricate structure, a testament to the grandeur of the universe, houses a myriad of celestial bodies, each with their own stories to tell. Within the Milky Way's expanse reside billions of stars, each differing in size, color, and age. Just like people, stars have their own life cycles. They are born, they live, and eventually they die. But unlike human lives, a star's life can span from a few million to a staggering trillion years. Let's start with dwarf stars. These stellar underdogs are the smallest stars in the universe, with masses reaching up to only 20% that of our Sun. But don't let their size fool you. Despite being small, they are incredibly dense and can burn for trillions of years, outliving most of their larger counterparts. Then we have the main sequence stars, like our Sun. These stars are in the prime of their lives, busy converting hydrogen into helium through nuclear fusion. This process generates enormous amounts of energy, lighting up these stars for billions of years. But all good things must come to an end. As main sequence stars exhaust their hydrogen supply, they evolve into red giants. These stars, now bloated and cool, begin to fuse helium into heavier elements. The Sun, too, will one day swell into a red giant, engulfing the inner planets in its death throes. In contrast to these giants are the neutron stars. These stellar remnants left after a supernova explosion are incredibly dense. So dense, in fact, that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. Now let's shift our gaze to star clusters and nebulae. Star clusters are groupings of stars, bound together by gravity. They're like stellar nurseries, where stars are born and grow together. These clusters can be either open, with a few hundred stars, or globular, housing up to 1 million stars. Nebulae, on the other hand, are vast clouds of gas and dust. These celestial nurseries are where stars are born. The gas and dust within these nebulae collapse under gravity, forming a dense core. This core, or protostar, then begins to heat up, eventually igniting nuclear fusion and giving birth to a new star. So, as we traverse the cosmos, we find an array of stellar populations, each with their unique characteristics and stories. From the smallest dwarf stars to the largest giants, from the densest neutron stars to the most vibrant nebulae, each star contributes to the grand tapestry of our galaxy. These celestial bodies scattered across the galaxy form a stellar symphony that lights up the cosmic stage. At the heart of the Milky Way lurks a cosmic beast, a supermassive black hole. This isn't a scene from a science fiction novel, but a fact of our universe. At the very core of our galaxy, amidst the dazzling luminosity and cosmic dust, lies a black hole named Sagittarius A*. It's about 4 million times the mass of our Sun, making it a supermassive black hole. Now you might wonder, how does this celestial monstrosity influence the dynamics of our galaxy? Well, its gravitational pull is so powerful that it holds the entire galaxy together. Just like children swirling around a merry-go-round, stars in the Milky Way orbit the supermassive black hole. The closer they are to the center, the faster they whirl. This dance of the stars, under the influence of the black hole, is what gives our galaxy its distinctive spiral shape. But let's not forget, the Milky Way isn't alone in the universe. It's part of a vast cosmic neighborhood filled with other galaxies. And sometimes these galaxies get a little too close for comfort. When galaxies collide, it's not like a car crash or an explosion. Instead, it's an intricate dance that unfolds over hundreds of millions of years. The galaxies pull at each other, distort their shapes, and eventually merge to form a larger galaxy. One famous example of this is the impending collision between the Milky Way and Andromeda, our nearest spiral galaxy. But don't fret. This celestial dance is about 4 billion years away. When it does happen, the supermassive black holes at the center of both galaxies will eventually merge, creating an even bigger black hole. Black holes also play a crucial role in galaxy formation. When galaxies collide, the intense gravitational interactions can trigger the formation of new stars. As these stars live and die, some will collapse into black holes. These black holes can then accumulate more mass, growing into supermassive black holes over time. Thus, through a cycle of creation and destruction, black holes contribute to the evolution of galaxies. So, what's the takeaway from all this? Black holes, despite their destructive reputation, are cosmic architects. They shape galaxies, drive star formation, and even play a role in the creation of elements necessary for life. They are a testament to the dynamic nature of the universe, where destruction paves the way for creation and chaos gives birth to order. From black holes to galactic dances, the Milky Way is a dynamic entity, constantly evolving in the vast cosmic arena. So next time you look up at the night sky, remember the cosmic labyrinth that lies beyond our vision, a place where stars are born, galaxies dance, and black holes rule. From its spiral arms to its supermassive heart, the Milky Way is a marvel of cosmic engineering. We've delved into its structure, explored the diverse stellar populations, and pondered the enigmatic black holes that govern its dynamics. Each aspect, a piece of the puzzle that makes up our galactic neighborhood. As we continue to unravel its mysteries, one thing is certain. The Milky Way is our cosmic home, a testament to the grandeur of the universe and our place within it. Imagine a cosmic ballet with billions of dancers, each performing their unique dance around a radiant star. Those dancers are exoplanets, planets beyond our solar system, orbiting stars far off in the cosmic sea. They pirouette in the darkness of space, far removed from human sight, yet captivating our curiosity and fueling our quest for understanding. The universe is an enormous stage filled with galaxies, stars, and celestial bodies performing a grand cosmic dance. It's vast, so vast in fact that comprehending its sheer scale is beyond our human capacity. Yet, within this immense cosmic playground, there are billions of stars like our Sun, each potentially hosting its own planetary system. These alien worlds, or exoplanets as we call them, are a source of both wonder and intrigue. They present us with the tantalizing possibility of life beyond our home planet. Could there be another Earth out there, tucked away in the far corners of the universe? Or perhaps something even more extraordinary? A world unlike anything we can even imagine. Each exoplanet is a mystery, a riddle waiting to be solved. They exist in an array of sizes, compositions, and climates, from gas giants larger than Jupiter to rocky planets smaller than Earth. Some are scorchingly close to their stars, while others inhabit the frigid outer reaches of their systems. Yet, each one holds a unique story, a piece of the cosmic puzzle that we strive to decipher. The study of exoplanets is a relatively young field in astronomy, having only begun in earnest in the late 20th century. Yet it has already yielded fascinating insights and challenged our understanding of the universe. It's a testament to human ingenuity and our insatiable curiosity about the world beyond our own. The universe is vast, and with billions of stars like our Sun, the possibility of other worlds, even of life, is an intriguing and exciting prospect. As we continue our cosmic dance, we look outwards, eager to uncover the secrets of these distant dancers and perhaps, one day, join them in their celestial ballet. So, how do scientists spot these distant dancers in the cosmic ballet? Let's delve into it. The first method is like playing cosmic peekaboo. It's called the transit method. Imagine a far-off star twinkling in its lonely corner of the universe. Suddenly, a tiny shadow passes across its face. This slight dimming of the star's light is a telltale sign that an exoplanet is making its grand entrance. This dip in brightness is measured and recorded, and voila, we've detected an exoplanet. Now, let's switch gears to the radial velocity method. This technique is a bit like a cosmic tango. As an exoplanet orbits its star, it doesn't just passively go around. No, it engages in a gravitational tug-of-war with the star. This causes a slight wobble in the star's position. The wobble might be small, but it's just enough to cause a shift in the star's light spectrum, which scientists can detect. Think of it as a celestial dance move, with the star and planet locked in a rhythmic sway. Finally, let's talk about direct imaging. This method is akin to snapping a family portrait of a star and its surrounding exoplanets. It's the most straightforward method, but also the most challenging. Why? Because stars are incredibly bright and their planets incredibly dim. It's like trying to spot a firefly buzzing around a spotlight from miles away. But with advanced technology and a bit of cosmic luck, scientists have managed to directly image a handful of exoplanets. Each method, with its own set of challenges and rewards, allows scientists to discover and study these far-off worlds. From the cosmic peekaboo of the transit method, to the gravitational tango of radial velocity, to the challenging family portrait of direct imaging, the search for exoplanets is a multifaceted endeavor. Each of these methods provides a unique lens through which we can observe and learn about these distant worlds. Now, what makes each dancer in this cosmic ballet unique? Just like dancers on a stage, each exoplanet has its own distinctive characteristics that make it stand out in the cosmic dance. These traits include size, composition, and position in relation to their host star. Let's start with size. Exoplanets can range from smaller than Earth to larger than Jupiter. Some are rocky like our home planet, while others are gas giants. Size is a crucial factor in determining an exoplanet's atmosphere, gravity, and potentially its habitability. Next, we consider composition. What an exoplanet is made of can tell us a lot about its history and how it was formed. Some planets are rich in heavy elements, suggesting a violent past of collisions and accretion. Others might be water worlds with vast oceans that could potentially harbor life. Now let's talk about the Goldilocks zone. In the world of exoplanets, this is the habitable zone around a star where the conditions could be just right, not too hot, not too cold, for liquid water to exist on the surface. It's a sweet spot where life as we know it might find a foothold. But remember, being in the Goldilocks zone doesn't guarantee that a planet is habitable. It just means it's possible. Here's where it gets even more interesting. Each of these factors, size, composition, and position, interact in complex ways. For instance, a large gas giant in the Goldilocks zone might not be habitable itself, but it could have moons that are. And let's not forget that these are just the characteristics we can observe from billions of kilometers away. Who knows what surprises these distant worlds might have in store for us? In the grand scheme of things, every exoplanet is a new world with its own unique properties and potential for hosting life. Each one is a fresh opportunity to expand our understanding of the universe and our place within it. So, let's keep exploring. Let's keep dancing with the stars. After all, the cosmic ballet goes on. Every exoplanet is a new world with its own unique properties and potential for hosting life. Can we peek into the atmospheres of these distant dancers? A tantalizing question indeed. The atmospheres of exoplanets, those mysterious celestial bodies spinning in a cosmic ballet far beyond our solar system, hold a wealth of information. They are gateways into understanding the conditions that exist on these distant worlds. Just as we study Earth's atmosphere to understand our own climate and weather patterns, scientists use similar principles to examine the atmospheres of exoplanets. The process is complex and requires a great deal of precision. Scientists observe these planets as they cross in front of their host stars. During this transit, some of the star's light filters through the planet's atmosphere. This filtered light carries with it the signature of the atmosphere's composition. Scientists then analyze this light to determine what elements make up the exoplanet's atmosphere. But the atmospheres of these distant dancers are not just a collection of gases. They also hold clues to the possibility of life, known as biosignatures. These biosignatures are certain chemical compounds, such as oxygen or methane, that are associated with biological processes. If we detect these chemicals in an exoplanet's atmosphere, it might suggest the presence of life. However, finding these biosignatures is an arduous task. They are often hidden among other chemical compounds and require sophisticated technology and innovative methods to tease out. But the reward, it could be the first sign of life beyond our own pale blue dot. And so, the search continues. The hunt for biosignatures is a meticulous process of sifting through data, of searching for that needle in a cosmic haystack. It's a scientific endeavor that requires patience, tenacity, and above all, curiosity. So, can we peek into the atmospheres of these distant dancers? Yes, we can, and we do, in the hopes of uncovering their secrets, of understanding their stories, and perhaps, just perhaps, answering that age-old question, are we alone in the universe? Studying the atmospheres of exoplanets and hunting for biosignatures is like trying to read the story of these worlds and possibly of life beyond Earth. The cosmic ballet continues, with new dancers joining every day. We've journeyed through the cosmic dance of exoplanets, seen the techniques used to spot these distant dancers, and explored the unique properties that make each one so intriguing. And yet, even as we pause to catch our breath, the dance goes on. We live in a universe that is vast beyond comprehension, a cosmic stage filled with countless stars, each potentially hosting its own family of exoplanets. These distant worlds, these celestial dancers, whirl around their stars in a silent symphony of cosmic motion. And every day, our understanding of this grand spectacle grows a little more. The search for alien worlds is more than just an academic curiosity. It is a testament to our innate desire to push the boundaries of our knowledge and explore the unknown. With each new exoplanet we discover, we get a fresh perspective on our own place in the cosmos. We've learned that the universe is abundant with exoplanets, some of them orbiting within the habitable zones of their stars, where conditions could be just right for life as we know it. We've discovered worlds of gas and ice, lava and rock, and some that defy all our expectations. The methods we use to detect and study these exoplanets, whether it's watching for the subtle dimming of a star as a planet passes in front, or measuring the slight wobble caused by a planet's gravitational pull, are feats of scientific ingenuity. They allow us to peer across the light years and gather clues about these alien worlds. But even with all we've learned, there is still so much more to discover. With every new technology, every new observation, we peel back another layer of the cosmic onion, revealing a universe that is more complex, more diverse, and more beautiful than we ever imagined. As we continue to explore the cosmos, every new exoplanet discovered is a step closer to answering the age-old question, are we alone in the universe? Have you ever pondered the mysteries of the universe, the unseen forces that govern everything we see? We begin our journey today, not with what we can see, but what we can't. The universe as we know it is made up of more than just stars, planets, and galaxies. There's an invisible, mysterious substance, a cosmic glue, if you will, that holds everything together. We call this enigma dark matter. Dark matter is estimated to make up approximately 85% of the matter in the universe. A staggering figure, isn't it? Yet, its existence is inferred through its gravitational effects on galaxies and galaxy clusters. It's like a silent puppeteer, pulling the strings of celestial bodies from behind the cosmic curtain. But why is dark matter so important? It's the key to understanding the structure and expansion of our universe, the blueprint of cosmic evolution. As we delve deeper, we will unravel more about this unseen cosmic enigma. Now let's dive into the fascinating world of dark matter. Dark matter, an unseen entity, has a profound impact on our universe. This elusive substance, which makes up about 85% of the matter in our universe, is something we can't see or touch, yet its influence is all around us. While the name dark matter might sound mysterious, it's simply a term for something that doesn't interact with light or any other form of electromagnetic radiation. So how can we be sure it exists? The answer lies in the way dark matter affects the motion of galaxies and galaxy clusters. You see, these cosmic structures move under the influence of gravity. The more mass an object has, the stronger its gravitational pull. When we calculate the gravitational effects based on the visible matter in galaxies, we realize that there's just not enough mass to account for their observed motion. So, where's all the extra gravity coming from? That's right, dark matter. It's the missing piece of the puzzle, providing the additional gravitational force that holds galaxies and galaxy clusters together. Now, if dark matter is invisible, then how do we detect it? Well, the answer is we don't. At least not directly. Scientists are like detectives, using indirect methods to infer its presence. They study the way light from distant galaxies bends as it passes through regions of space filled with dark matter, a phenomenon known as gravitational lensing. But that's not all. There are numerous experiments happening right now, deep underground and in space, to detect dark matter particles directly. These experiments are based on various hypotheses about what dark matter might be made of. Some suggest it could be composed of weakly interacting massive particles, or WIMPs, while others propose it could be made up of axions, hypothetical particles with a tiny mass. However, despite our best efforts, dark matter continues to elude direct detection. We're still not sure what it's made of, and that's one of the biggest unsolved mysteries in physics today. But don't be disheartened. The quest for understanding dark matter is a journey, not a destination. And every step we take, every experiment we conduct, brings us closer to unraveling its secrets. So, dark matter, despite being invisible, plays a crucial role in the structure and dynamics of the universe. It's a testament to the fact that sometimes the things we can't see are the ones that matter most. With every passing day, we continue our cosmic detective work, piecing together the puzzle of our universe, one clue at a time. And who knows, perhaps one day we'll finally shine a light on the enigma that is dark matter. From the invisible matter, we move on to an invisible energy, dark energy. Dark energy is a term that may sound like it's straight out of a science fiction novel. However, it's a scientific concept that plays a crucial role in our understanding of the universe. It's an invisible force, a form of energy that permeates all of space and is believed to be the key player in the accelerated expansion of the universe. Our knowledge about dark energy is in its infancy, and yet it's estimated to make up about 70% of the universe. That's right, most of the universe is made up of something we can't see, touch, or fully understand. But how do we even know it's there if it's so elusive? The story of dark energy begins with the discovery that the universe is not just expanding, but the rate of its expansion is accelerating. This was a startling revelation, contradicting the then prevalent belief that the expansion of the universe should be slowing down due to gravity. To explain this unexpected acceleration, scientists proposed the existence of a mysterious energy that works against the pull of gravity on a cosmic scale. They called it dark energy. But remember, dark in this context doesn't mean it's literally dark. It's dark because it's unknown and mysterious. Now, let's talk about two significant pieces of evidence that hint at the existence of dark energy: the cosmic microwave background studies and supernova observations. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. It's the oldest light in the universe, and studying it provides us with a snapshot of the universe shortly after its birth. The pattern of tiny temperature fluctuations in the CMB can give us a wealth of information about the composition and evolution of the universe. And guess what? The data points towards a universe dominated by dark energy. Next, we have the supernova observations. Supernovae are the explosive deaths of stars, and they can be so bright that they outshine their host galaxies. By observing a particular type of supernova known as type Ia, scientists found that the distant supernova were dimmer than expected. This suggested that the universe's expansion has been speeding up over time. And the culprit behind this accelerated expansion? You guessed it, dark energy. In the grand cosmic puzzle, dark energy is a piece that doesn't quite fit yet. It's a concept that challenges our understanding of the fundamental laws of physics. But it's also a testament to the beauty of science, a reminder that there's always more to learn, more to discover. Thus, dark energy, the mysterious force, is driving the universe's accelerated expansion. The existence of dark matter and dark energy has far-reaching implications for our understanding of the universe. As we delve into the fourth and final chapter of our journey, let's explore the potential future of our universe, shaped by these unseen entities. Dark matter and dark energy are not just fascinating puzzles for scientists to solve. They shape the universe as we know it, influencing the formation of galaxies and the expansion of the cosmos. But what does this mean for the future? Currently, our universe is in a state of accelerated expansion, a phenomenon attributed to dark energy. If this expansion continues unchecked, we might be heading towards a future cosmological event known as the Big Rip. This theory suggests that the fabric of space-time could be pulled apart by the ever-increasing influence of dark energy, ripping apart everything from galaxies and stars to atoms themselves. On the other hand, if dark energy weakens over time or reverses its behavior, we might be facing a big crunch. This is the exact opposite of the Big Rip, where the universe would contract, collapsing in on itself due to the gravitational pull of dark matter and other matter in the universe. However, it's also possible that our understanding of dark matter and dark energy isn't complete. There are multiple alternative theories being explored that could drastically change our predictions for the future. Some researchers have proposed that dark matter and dark energy are manifestations of a deeper, still unknown aspect of physics. Others suggest that they could be evidence of extra dimensions or a multiverse. These theories, if proven, would revolutionize our understanding of the universe. Despite the uncertainty, what's clear is that dark matter and dark energy play a crucial role in the evolution of our universe. The destiny of the cosmos is entwined with these mysterious forces, and our fate may well be sealed in their shadowy grasp. The quest to understand dark matter and dark energy is more than just academic curiosity. It's about understanding our place in the universe and our ultimate destiny. It's about answering some of the most fundamental questions we can ask. Where did we come from? Where are we going? What is the nature of reality? The road to these answers is long and winding, but every step we take brings us closer to the truth. As we continue to probe the mysteries of the cosmos, we uncover new questions, new puzzles to solve. But that's the beauty of science. It's a never-ending journey of discovery, a testament to our insatiable thirst for knowledge. In the face of these unseen forces, science continues its quest to unravel the mysteries of the universe.
Picture the universe, vast and infinite. Now imagine it reaching its end. Yes, you heard that right. The universe's end. It's a captivating yet daunting concept, isn't it? The universe, with all its galaxies, stars and planets, meeting an eventual demise. But how could that be? How could something so vast and seemingly endless simply cease to exist? Well, it's not as simple as flipping a switch. The fate of our universe is a topic that has fascinated scientists, philosophers, and thinkers for centuries. And with modern scientific advancements, we're beginning to unravel some of the mysteries. There are several theories about how the universe might meet its end. Some propose a chilling future, others a fiery one. Some even suggest an ever-expanding universe that gradually fades away. So, are you ready to delve into the deep cosmos and explore the fascinating theories about the universe's fate? Ever since the Big Bang, the universe has been expanding. But what exactly does this mean for the universe's future? To understand the universe's expansion, we first need to take a step back to about 14 billion years ago. Picture this: an incredibly hot and dense state, smaller than a single atom. This is where it all began, the Big Bang, a momentous explosion that sent matter, energy, space, and time hurtling outwards. This marked the inception of our universe as we know it. As time ticked on, the universe started to cool and expand, a process that continues to this day. Imagine a balloon being inflated. As more air enters the balloon, the surface expands and the dots marked on it move away from each other. Similarly, in our universe, galaxies are drifting apart as space itself expands. But here's a twist in the tale. Our universe isn't merely expanding, it's doing so at an accelerating rate. This was a surprising discovery made by astronomers in the late 20th century. The culprit, a mysterious cosmic phenomenon known as dark energy, which is believed to be driving this accelerated expansion. So what does this mean for our universe's future? Well, if the expansion continues to accelerate, galaxies outside our own will gradually recede from view. Eventually, the night sky will become devoid of distant galaxies, leaving us in a rather lonely cosmic neighborhood. Moreover, if this accelerated expansion continues indefinitely, it could lead to a scenario known as the Big Rip. In this scenario, the universe's expansion becomes so extreme that it starts to tear apart everything in its path, from galaxies and stars to atoms and subatomic particles. Quite a dramatic ending, isn't it? But remember, these are just theories, and our understanding of the universe is ever evolving. As technology advances and our knowledge deepens, who knows what new discoveries await us in the vast cosmic expanse. So, the expansion of the universe could lead to some intriguing possibilities. Let's explore them. One possible fate of the universe is the Big Freeze, a scenario that could turn the universe into a cold, dark place. This is not a scene from a science fiction movie, but a legitimate scientific theory about the potential end of the universe as we know it. Let's dive into the details. Picture the universe as a vast expanse, constantly expanding. This expansion is driven by a mysterious force we call dark energy. With time, as the universe expands, galaxies are drawn apart from each other. This results in a decrease in the density of matter and energy in the universe. Now let's bring stars into the picture. Stars are the powerhouses of the universe, radiating energy and heat. They are fueled by nuclear fusion, a process that combines lighter elements to form heavier ones, releasing energy in the process. However, they can't burn forever. Over billions of years, stars will exhaust their nuclear fuel. At this point, stars will begin to die, their light and heat gradually fading away. As more and more stars burn out, the universe will become darker and colder. This is the beginning of the Big Freeze. But what about matter? Well, even matter won't last forever. Protons, the stable particles in the nucleus of an atom, are thought to decay over an unimaginably long time scale. When the last proton decays, matter as we know it will cease to exist. So imagine a universe devoid of stars, a universe where matter has decayed into nothingness, a universe that has expanded so much that it is virtually empty. The temperature will approach absolute zero, the theoretical lower limit of the thermodynamic temperature scale. This is what we refer to as the Big Freeze, a state of endless frigid darkness. A chilling prospect indeed, but not the only one. Another theory suggests a much more dramatic end, but that's a story for another time. For now, let's ponder the icy silence of the Big Freeze. The Big Crunch theory proposes a universe that eventually stops expanding and starts contracting. Let's dive into this fascinating hypothesis. You see, the Big Crunch theory is essentially the exact opposite of the Big Bang theory. Rather than a universe that began with an explosion and has been expanding ever since, the Big Crunch theory suggests a universe that will eventually stop expanding and start contracting. Imagine blowing up a balloon, but instead of popping, the balloon begins to deflate, gradually returning to its original size. That's exactly what the Big Crunch theory proposes for our universe. Currently, we're in the expansion phase, akin to the balloon being blown up. But what if gravity, that ever-pulling force, eventually overcomes this expansion? Gravity, as we know, is a force of attraction. It pulls objects towards each other. Right now, the universe is expanding faster than gravity can pull things back together. But if the universe's expansion were to slow down, gravity would begin to pull everything back towards the center. Think of it as a cosmic tug of war, with the universe's expansion on one side and gravity on the other. For now, the universe's expansion is winning, but according to the Big Crunch theory, gravity might eventually win this cosmic game, causing a universe-wide contraction. And what happens when the universe contracts? Well, everything in the universe would start moving closer together. Galaxies would merge, stars would collide, and eventually everything would condense into a single point of infinite density, a scenario reminiscent of the state of the universe before the Big Bang. This would result in a fiery, chaotic end to the universe as we know it. An event so cataclysmic, it's hard to fathom. But remember, this is just a theory, one of many that attempt to predict the fate of our universe. A fiery end indeed, but there's one more theory we need to discuss. Finally, we have the Big Rip, a theory that suggests the universe could tear itself apart. Imagine a scenario where the very fabric of space-time is pulled apart at the seams. This is the essence of the Big Rip theory. This theory hinges on the idea that the universe's expansion is not only continuing, but is also accelerating at a rapid pace. This acceleration is driven by a mysterious force known as dark energy. Although we don't fully understand what dark energy is, we know it's powerful enough to counteract the force of gravity that holds galaxies, stars, and even atoms together. If the force of dark energy continues to increase, it could eventually overwhelm gravity entirely. At that point, the universe would not just be expanding, but ripping apart. Galaxies would be the first to go, torn apart as the space between stars expands too fast for gravity to hold them together. After that, individual stars and planets would meet the same fate, followed by smaller structures like asteroids and then molecules. But the Big Rip wouldn't stop there. If the theory holds true, even atoms, the basic building blocks of matter, would be ripped apart in the final moments of the universe. Imagine a scenario where every atom that makes up everything we know, from the vast cosmos to our own bodies, is torn apart. It's a chilling thought, isn't it? However, before we get too carried away, it's important to remember that the Big Rip is just one of many theories about the fate of the universe. It's based on our current understanding of the universe and the forces at play, which is always changing as we learn more. A terrifying prospect, but remember, these are just theories. The universe's fate is still a mystery, which makes the study of cosmology all the more fascinating. So, we have explored some intriguing theories about the universe's fate. We delved into the concept of the universe's expansion, a phenomenon that continues to shape our cosmic surroundings. We learned about the Big Freeze theory, which hypothesizes a universe slowly cooling down, reaching a state of maximum entropy where all life and motion cease. Then we ventured into the Big Crunch theory, which presents a scenario of the universe collapsing into a singularity, a reversal of the Big Bang. We also discussed the Big Rip theory that paints a picture of a universe torn apart by its own accelerating expansion. These are just theories, speculations based on our current understanding and observations. They invite us to challenge our perspectives and ponder on the grandeur of the cosmos. But as we explore and learn more, our theories may change, evolve, or even be replaced by new ones. The universe's fate remains a captivating mystery, a testament to the infinite possibilities that lie within the cosmos.